Okay, so for Gaussian channel, I'm not going to I'm going to use, so this is an intermediate analysis. So I'm going to use whatever off-the-shelf good codes for common and private. So I'm going to code my common messages and private messages using different channel codes, independent channel codes, and we're going to add up them together and send all the error. Yes. But the important thing is, how do I split the power? Because I have a limited power at the transmitter. I have power constraint. How do I split the power for my common signals and my private signals? And the design guideline here is to set the private, to make the private signals goes below the
noise level of the
other receiver. And the coding is, you can use whatever good channel codes.
It's below the noise level, and because you get the attenuation from the cross-link, it's hidden.
Yeah.
So you have to know the channel, as you said, you have
yeah,
to know the channel attenuation in advance, and then you can use this approach.
Yes. As I said, so if I want to use this, even on this scheme, then transmitter 1 has to know what's the cross-link channel it goes from transmitter 1 to receiver 2. Because we want to guarantee that the private signal is going to be goes below the noise level after the attenuation of the cross-link from transmitter 1 to receiver 2. So he has to know, or she has to know the cross-link from transmitter 1 to receiver 2. Okay. So this is basically the intuition that we have from the study of interference channel without cooperation. So now with cooperation, as I said, I don't want the private information to get polluted in my exchange information among receivers. So I'm going to use a very simple quantization to quantize at the private signal level so that I can reject all the private signals. So now notice that for receiver 2, the private signal from user 1 is not of its interest because receiver 1 do not want to decode the private user 1's private signal, which is red 1. Right? So I should not include any of these red 1 signals into the exchange information from receiver 1 to receiver 2. So what I do here is I just quantize your received signals at the private signal level. So the private signals in your direct link has some certain power, right? For example, 10 dB or something. I'm going to quantize at that level so that I can reject all the signals below. So no private signals will go into the exchange information. Okay. So after this quantitation, I'm going to do, because I may not have enough capability to convey the exact quantitation point. So I'm going to do some partitioning on the quantitation bits, quantitation points, and just convey the bit index to the other receiver. So after that, I do joint decoding using my own receive signals and these bit index to decode my desired messages, which are the common messages and your own private message. And this strategy achieves the symmetric capacity within 3 bits universally. So this is optimal for the symmetric case. So now, beyond one run, is this one run strategy sufficient to achieve the capacity in general, capacity region in general? And notice that in the previous strategy, we discard all the information below the private level. Okay?
That's strictly for the cooperative regime, right?
Yes.
Yeah.
Yes. So in the symmetric case, there's no useful information below the private level. So this strategy would be optimal. So I can achieve the capacity within the constant number of bits. Okay. So this is not true in general. So consider this asymmetric example in the linear deterministic model. So I want to support 3 bits for user 1 and 1 bit for user 2. So I turn on the bits like this. Okay. Notice that the bit A3 is never appearing at every single one because of this special channel structure. So I'm going to, I will need So there are some useful information lies below the primary signal level at receiver 2. Okay, so for user 2, I can simply send A2 to receiver 2. I can get rid of the interference. I can get bit B2 for user 2. But for user 1, I have to convey this A3 to receiver 1. Okay? And this is the case where I have some useful information lies below the primary signal level. So in some sense, I would need to have some, and the previous scheme cannot do this because in the previous scheme, receiver 2 will quantize at the private signal level. And all the bits below the private signal level is going to be gone. In this example, the 2 LSBs is going to be gone at receiver 2. So I cannot convey A3 to receiver 1. So in some sense, in the Gaussian channel, I will have to find out some mechanism to extract the useful information below the private level. In this example, it's a bit A3. Okay? And it turns out that you can have a simple two-round strategy to achieve this. So in this two-round strategy, receiver 1 first quantizes at the private signal level, bin and towards the bin index, as I described in the previous slide, and then convey the bin index to receiver 2. But receiver 2 has to first decode its desired messages and bin the count messages and then forward the bin index back to receiver 1. So basically, I'm forming some random linear equations using the count messages, okay, and decode. And it turns out that this strategy can achieve the capacitor region to within 2 bits universally, regardless of function parameters. So this is the main theorem of this work. And the two-round strategy means a huge delay because to achieve the channel capacity for point function, I would have to use a long block length of the code, channel code. Right? So if I have to wait 2 rounds, then that's a huge delay for the users. So I would like to say that maybe in some special cases, like in the symmetric case, 1 round is sufficient. And this is the theorem that at a strong interference, the 1 round strategy is sufficient to achieve the capacity region within 1 bits universally. Within 1 bit universally. That's at a strong interference region. So that's the work I did for receiver cooperation. So we characterize the gain from receiver cooperation.
And this carried you through which exam? This carried you through which exam?
This used my qualified. Yes. So in this work, we characterize the gain from receiver cooperation in this simple 2-user setting. And the characterization is both qualitatively and quantitatively. So quantitatively, I can have this degrees of freedom gain in the power gain. This linear region and this saturation region. And in the saturation region, it's at most 1 bit of power gain. And in the linear region, it's either 1 by 1 or 2 by 1. That's the result. So transmitter cooperation.
Sorry,
Yes.
but in example you show of 2 cooperation bits, you also need 2 rounds, right?
In my symmetric example,
Yes.
actually no, because
In a non-symmetric example, you get
in the non-symmetric example, I was doing 2 rounds.
In this one?
In this one, yeah,
Yes.
you don't need 2 rounds.
No, because you decode
Yeah, that's for
A2, then A2, you transmit A2.
yes, that's right.
2 rounds.
But you can actually achieve that using only 1 round. For example, you can so in this situation, you can send B1 to receiver 1, and simultaneously you can send A2 plus B1 to receiver 2. Right? And also at receiver 2 you have 4 equations, which is
you have
B1,
B1
A1, B3 plus A2